Hi, my name is Leila, and I'm a fifth-year PhD student at Boston University. Today, I'm going to talk about our paper titled PHMon, a programmable hardware monitor and its security use cases. This work is in collaboration with my colleagues Sadullah, Boyou, and Schuyler, as well as my advisors Professor Ajay, Joshi, and Professor Manuel Egele. In recent years, there has been a growing trend in the industry to enforce new security extensions in hardware, such as Intel MPX and Intel CT. These extensions are typically faster than software-based approaches, but their implementation requires a long and expensive process, and then we end up with fixed security policies built in silicon that cannot get updated as security threats evolve. And if there is any problem in the hardware implementation, then we have to wait for the next generation of the processors until the problems get fixed. To clarify the challenges involved in adding a new security extension in hardware, let's take a look at an example. We all know that the C programming language suffers from memory safety issues, and researchers have been trying to address this problem since a long time ago using software-based approaches like SafeC in 1994 or hardware-based approaches like Hardbound in 2008. Finally, in 2013, Intel announced that they're going to include a new hardware extension called MPX for memory bound checking to assist with addressing this problem. And it still took 2 more years until MPX was commercially available on the processors, but things didn't go as expected after that. There has been reports about compatibility issues of MPX with legacy programs, as well as performance issues where MPX could incur a considerable performance overhead, even up to 4 times in some cases. Because of all these issues, after a while, LLVM, GCC, and Linux kernel all announced that they're going to stop supporting MPX, and by 2019, MPX was disabled. This example clearly shows how challenging it is to add a new security extension in hardware. But what if rather than having a fixed security policy built in silicon, we could have a flexible hardware implementation that could enhance and enforce a variety of security policies as security threats evolve? In this way, we could gain both flexibility and efficiency. This is exactly what we are trying to do in our proposal of a programmable hardware monitor called PHMon. PHMon is a hardware monitor and the full software stack around it. In our design, we leverage the free and open RISC-V instruction set architecture, and we interface our hardware monitor with an open source RISC-V Rocket processor. Then we provide the operating system support for our hardware, and in addition to that, we provide a software API to communicate with our hardware. When we have all these layers, we leverage our hardware monitor for a variety of security use cases. This figure shows the general overview of how PHMon works. As a first step, a user or admin configures the hardware monitor to look for specific events, for example, detecting all the branch instructions during the program execution. At runtime, PHMon monitors the execution and looks for those specified events. Whenever it finds a match, then it performs a follow-up action, for example, ALE operation. The monitoring events and taking actions is a continuous process until PHMon is disabled or the process is terminated. But what are the events that PHMon can monitor and the actions that it can perform? To answer this question, let's take a look at the hardware overview of PHMon. At the hardware level, PHMon is responsible for collecting the instruction trace. To do this, we minimally modify the write-back stage of the pipeline in the RISC-V Rocket course pipeline to collect the execution trace in the form of a commit log. We send the commit log information to PHMon. The commit log shows what instruction got executed, what's the corresponding program counter, what's the next value of the program counter, and what are the address and data corresponding to this instruction if, for example, we have a load store instruction. PHMon consists of 2 main units, a number of match units or MUs, and an action unit. Each match unit is responsible for monitoring a specific event, and an event is identified by specific patterns on each of the commit log entries. For example, a user might be interested in monitoring all the call instructions in a range of memory addresses. This can be our event. Whenever PHMon finds a match with that event, then it performs a series of follow-up actions specified by the user. These actions could be in the form of arithmetic and logical operations, sending a memory request to the L1 data cache through the ROC interface, or triggering an interrupt that will be handled by the operating system. To be able to use PHMon, we need to provide a software API for it. And we do this by leveraging the RISC-V custom instructions. We provide a list of functions that the user can use to configure PHMon and communicate with it. For example, here you can see a function that we can use to reset PHMon and then configure a monitoring pattern on it. Here you can see an example of how we can configure PHMon to perform an action. More specifically, the action here is comparing the value of PC destination and PC source stored in local registers, and then if these values don't match, we will trigger an interrupt. To enable per process monitoring capability, we have to provide DOS support for PHMon, and we do this by modifying the task struct in the Linux kernel to maintain PHMon's information during context switches. In addition to that, whenever PHMon triggers an interrupt, we delegate the machine-level interrupt to the operating system, and we provide the interrupt handling OS support by terminating the violating process. To be able to use PHMon for our security use cases, we need to have a prototype of it. We implement PHMon as a Rocket custom coprocessor written in Chisel hardware description language, and we interface our design with the RISC-V Rocket core. We modify the Linux kernel version 4.15 to provide the support for PHMon. Then we prototype our full design on a Z-board FPGA. We leverage the RISC-V GNU toolchain to cross-compile our benchmarks and run them on our FPGA. We have already open sourced our design and source code in this GitHub repository, so please take a look at our GitHub repository if you're interested in our work. PHMon is versatile and easy to adopt for various use cases, and in our paper we show this using 4 different use cases. A shadow stack, a hardware-accelerated fuzzing engine, preventing information leakage, and watch points and accelerator debuggers. But because of the limited time, today I'm only going to talk about the shadow stack use case and the hardware-accelerated fuzzing engine. Please refer to our paper for more information about all of our use cases and our full evaluation results. Let's start with the shadow stack use case. As you know, shadow stack can be used to prevent return-oriented programming attacks, and we can simply program PHMon to act as a shadow stack using 2 match units. One match unit can monitor the call instructions, and another match unit can monitor return instructions. Then both of these match units can read and write into a shared memory space allocated by the operating system. But why is it interesting to have a PHMon-based shadow stack? So first of all, our design is flexible and it's not fixed in silicon. And second, we can provide a secure shadow stack, meaning that we can guarantee the integrity of the shadow stack memory. To do so, we can leverage another match unit to monitor the shadow stack memory region and to make sure that PHMon is the only one who can read and write into this memory region, and this way prevent the shadow stack memory from getting corrupted. And on top of all of these, our implementation is efficient. We have evaluated our PHMon-based shadow stack on a range of spec 2000, 2006, and Mi-Bench benchmarks, and on average, PHMon has less than 1% performance overhead. As shown in this plot, the performance overhead of PHMon over a range of spec 2006 benchmarks is only 1.2% on average. Another use case for PHMon is a hardware-accelerated fuzzing engine. We looked into American Fuzzy Loop or AFL, which is a state-of-the-art fuzzer consisting of two main units, a fuzzing logic and an instrumentation suite. Whenever the source code is not available, AFL relies on QEMO for instrumentation. Or more specifically, QEMO collects the branch coverage information during the child process execution and updates a shared memory region accordingly. Then AFL reads this information and decides about the next fuzzing step. But because QEMO is a software-based emulator, it incurs considerable performance overhead. That is exactly where PHMon comes into the picture. We can replace QEMO with PHMon, and PHMon can monitor the execution of the child process and collect the same branch coverage information and write the results into a shared memory region. But because PHMon is a hardware-based implementation, it can improve the performance of AFL. As our result shows here, over a range of benchmarks listed on the AFL website, PHMon improves the performance over the baseline QEMO-based AFL by 16 times, while our hardware only had 5% power overhead and around 13% area overhead. With this example, I'd like to finish my presentation. To conclude, in our paper, we propose a hardware monitor with the full software stack. PHMon is versatile and easy to adopt. We have a full FPGA prototype of our design. Our paper is artifact evaluated. We have open source our code on a GitHub repository. And thanks a lot for your attention. If you have any further questions, please send me an email. Thank you.